Hello and welcome to my presentation, SentimentNet, which is mood-based music generation using machine learning. Here's an outline of my presentation. Let's talk about situation and project goals first. First, let's consider a music composer wants to create a background music for his movie, which portrays an emotion for a scene in the movie. So he composes the music, but is not so satisfied with what the music has been created and would like to explore more options around the same theme. And composing these kind of music, which is around similar to the same theme and has different emotion attached to it, is a tedious task. And this is what we would like to achieve using our machine learning models. So the goals over here is to analyze the music, which is based on audio parameters and performance level parameters, and then generate multiple alternatives to this original music, which has a different emotion and but still keeps the underlying theme intact. So the approach that we follow here is first we created a label data set of 170 songs, which was got from MusicNet. This data set already had performance level score parameters along it, but we label these files in terms of happy, sad, and suspenseful emotions, which are common emotions in music scenes. Then we developed a model called SentimentNet, which learns music parameters such as patterns in terms of notes and also the performance score and the emotion of that music. After this, the SentimentNet is able to predict new music sequences, and it's also evaluated on basis of similarity using fuzzy algorithms and spectrum plots. Here are the three different types of representation of music among many different available. First is the piano roll or the sheet music. So this sheet music is a common representation used by composers to note down musical notes on paper. The next is a common wave plot. The y-axis represents amplitude and x is just the time. Last one is a piano roll in terms of a MIDI file, and this is the mapping of all three files. So now input to our SentimentNet is going to be a music file in terms of piano roll, along with the mood that is required for the output, right? And the output would be a new music which has that mood that the user expects. First spectrogram is actually created by the model, and then later it returns a wave file which is audible format. Here is the data that we have. So we have start, end time, instrument that was played, note that was played, note value, and then a semantic label that was added manually for the songs that we trained our model on. So to understand the train and test split, the entire data was first converted into 80-20 ratio for 80 for test, train purpose and 20 for split. Within the train again, 80-20 ratio was given for just the train and validation set for 20%. The first two graphs over here represent the epoch or average loss along the epochs during the training phase. This graph is for test loss. So if you notice first, this curve is reducing, but it's not really smoothly decreasing, and it is kind of wavy like that. The reason being that every time the model looks at a new music file, the music file is starkly different from the previous music file that it was trained on. Hence, the loss is not really consistently decreasing downwards. This contributes to the differences in different music files that the model was trained on. Next, going to the loss values, the best minimum loss was achieved at 288th epoch for train set, and for the test set at 250th epoch was the best loss. After the 290th epoch, the loss started increasing, and therefore, after looking at these two mapping and also the mapping for 258th set for the train set, we concluded that it would be a good idea to have our good epoch value set to 290. And then we also experimented around with batch size, showing accuracies, calculating accuracies along the way. And batch size was 128 for good accuracy and minimum loss. Now let's look at objective and constraints of our model. So first is no low latency requirement. So the result of the new music is not expected instantaneously, is what this means. The music composers could wait for some time while the music is being generated, as this is not a life and death situation, but the output should be fairly good sounding. So that is an important part. Uh, Interpretability of model is not required in terms of probability values, but we need to look at, we need to provide the music composers with similarity of the input file with the generated output. And also they should be able to make sure that there is a difference in different emotions that was generated every time by the model. For error analysis, if the model has a starkingly high and low errors, that can be a problem, but little errors here and there should not be a big problem, as it's not predicting something which is very much fixed. It's creation of new artwork. uh, the output features of the model should be obviously something usable. So it should be an audio file which can be directly played, rather than being something which requires different softwares to understand in terms of spectrogram. So these are objectives and constraints that we have considered. Now let's look at the model architecture that we are trying to build our architecture on. So this is the architecture of SentimentNet. What they have done is they have used this two different subnets for score to audio generation. Usually when people were using recurrent neural networks or LSTMs, they were actually doing it on audio to audio generation, where the machine learns audio features only. For our purpose, we want the machine to learn, or model to learn, audio features along with the score values and the sentiment labels. Therefore, it was a good idea to adopt this SentimentNet model. Um, First, there are two type of things that is happening over here. Uh, the model has to learn the image to image mapping. Um, that is the piano roll to spectrogram image mapping, and that is achieved from the contour net, which has an encoder decoder kind of an architecture. So encoder compresses the music, and decoder decompresses it. Basically, the input and output of this is the same thing, but this is how the music learns image to image mapping. The next one is really interesting because the input was in terms of piano rolls, and the output was spectrograms. These two matrices are very different in dimensionality. So the piano rolls are really small dimensionality matrix and sparsely populated, whereas spectrograms are dense matrix with very high dimensional values. Therefore, taking inspiration from computer graphics, this problem is an image super resolution problem, and which is solved by TextureNet. So what TextureNet does is allows the model to understand the mapping between piano rolls, which are low dimensional structures or matrices, and the spectrograms. TextureNet also allows the model to learn all these label features of the audio file, which is the score representation and the sentiment. Therefore, these two subnets together allow SentimentNet and our SentimentNet model, which is based on this, to learn different features, which is to learn label features, which is different from just the audio ones. The libraries that we have used to build our model are MusicNet, Music21, and Librosa for reading and processing the files. The CSV, or the label structure, is read in data structure called interval tree, coming from this Python library. And the model is built using Torch neural network, and data is split using skitlearn. Now let's look at the demonstration of our SentimentNet. So here is what I've created for the demonstration purpose. First, we'll understand the audio input file that we are giving for the model. I'll play the input file first. This is the K Sera Sera song. All right, so that's given as an input to our model, and let's look at what sad emotion the model generated. Obviously, the input is a happy song, therefore the sad sounds like that. So it's trying to do something, play around with the sad low notes, and that is what it created. Now this one is for the happy emotion. That is fairly happy and cleaner output, which is expected because our input file was originally happy. Now let's look at suspenseful emotion. This is interesting because the model has learned that suspense has kind of low amplitudes in the start, and then it suddenly has high amplitudes towards the end, and that is similar to what it has actually created for us. Here is the spectrogram plot for input file. The color represent amplitude, and then we have frequency at the y-axis. So this is our input file. That's the spectrogram for happy files. All of this is explained in detail in the report. So we can start noticing one thing over here though is for the sad emotion, it has taken something low at the beginning, and somehow it goes to a little high thing at the end, but that's the amplitude it's actually generating on, so everything is of a lower amplitude. For a happy music, there's a quite a different vibration in amplitude, so we have more of larger amplitudes in happy music, which is kind of expected that the model should have learned. For the suspense music, again here initially it has low amplitude. It's building up the complex suspenseful emotion, and at the end it has higher amplitude, which is kind of interesting to look at in terms of spectrogram. We've also used some decomposition techniques to understand how these spectrogram mappings happen. Um, and let's look at the similarity matrix at the end. So here is what we have achieved using the fuzzy logic package in Python. Here are the similarities of three emotion compared to the input file. So our input file was a happy song, happy one by nature, and the happy one has the highest similarity, then is the suspenseful, and then we have the sad one. So that's kind of the expected behavior of the model. Now let's have a discussion on the output features. So first is model interpretations. So the problem of music composition is a real world problem, and SentimentNet does a good job at suggesting composers as to what kind of emotions they are looking for, and it's easy to understand. The output can be played directly. For business changes, obviously, if we want to improve or implement this model, we need good computation power, which is for my model, I've used 2 GPUs and a really good CPU, and those things are well documented. And to update the model now, we would require to create the data set that has the semantic labels to it. So we might use automatic classification techniques for that, and that's how the model updates can actually happen if we want to. All right, so thank you for your time, and I hope you enjoyed your presentation.